super excited to be here today. So we are going to talk about learning generative models from corrupted and synthetic data. And this is a line of work that I have been doing for the past 2 or 3 years with Kostis, that was in the panel yesterday, with Adam, and a lot of other people. So thanks a lot to all of them. And let's get started. So we're going to be talking about generative models. So a natural first question is how do you train a generative model? What do you do? And it's actually a pretty simple strategy if you abstract it away. So there are 3 steps. In the very first step, you want to collect data. Maybe you go to the web, you download a bunch of images, a bunch of text. So this is your training distribution, or maybe you pay people to give you access to proprietary data. Then the second step is you want to go and you want to train your model. And then after you have trained your model, you want to use it for something. Maybe you give it an image of my PhD advisor, Alex Dimaki, some part of the image is missing, and then you ask your model, can you complete the missing part? And the model knows how real people look like. It has a prior about the world, so it's going to do this task for you. So what I want to argue today is on these 2 latter steps, there has been a lot of research. For example, if you want to train your generative model, you have to consider a bunch of things, am I going to use a diffusion? Am I going to use a net autoregressive model? How am I going to train this? What architecture am I going to use? There are a bunch of questions. And then even after you have trained your model, you want to use your model now to solve some problem. And there are all sorts of research questions about how do you use the prior in the model to solve your problem of interest. But the first step is super important, and I think it's kind of a fact that the secret in these amazing models that you see, and they generate pretty pictures and videos and all of that, is the data, right? If you have good data, you most likely are going to have a good model. If you don't have good data, you're not going to have a good model. And I want to argue this step is kind of not really well studied about how you do this. So how do you normally do it? There are a bunch of approaches, but on a high level, you will go on the web, you will download a bunch of things, and then you want to filter out the bad samples. You're gonna have things that are I don't know, low quality, they're gonna be duplicated, they're gonna be copyrighted, so you want to remove all that. And then after you remove all that, you train on the remaining, or maybe you train first on everything, and then you fine tune on this type of high quality data that survived your filtering pipeline. So it is a pretty simple strategy, and it has been working really well. And it has led to these massive data sets of millions or billions of images and text pairs that you use to train your models. And the success of these models is actually a function of these data sets that we create. Cool. So that's what happens usually. Now I want to argue that there are a lot of things that can go wrong in this attempt that we do to create these high-quality training data sets. And the very first thing that can go wrong is that if you want to do science, creating these large-scale data sets is actually quite challenging. For example, if you want to train an image generative model, you usually train it on I don't know, 10 billion of image text pairs. But if you want to do MRI, you want to find scans of brains. And if you go to the go-to repository for that, fast MRI, you're going to only find 6,000 of them. So that's not great, not nearly close to the scale that you would like to be. And if you want to do proteins, in proteins it's actually a very interesting case because each sample is a PhD. So someone spent 5 years crystallizing a protein, and then they have to make it and make the crystal, shoot X-rays, then from the X-rays and the diffraction data try to understand what the protein looks like. And this is a 5-year work. So it's actually pretty hard, and good luck if you want to have a billion PhDs. It's not going to happen. And even worse, if you want to do black hole images, you never observe a good sample. So you never observe the full measurements. So in this scientific application space, it's very hard to create these data sets. But even if you look at images, there is something that's very interesting that is happening. Even within a certain data set, your favorite data set, you're going to find samples that have different utilities and different qualities. For example, this is a data set that people use for training text-to-image models, and these are some bad samples, and you have to define what badness is. But I think we can all agree that these samples are much better, and they're samples from the same data set. And don't go too far, because this is happening in your favorite image in a data set that you have trained a lot of academic models on, like there are some low quality samples. These are like samples that have like blurriness, they're like severely compressed, they have poor lighting, and then there are like some high quality samples, okay? And then when you want to train your model, you're facing this dilemma. And the dilemma is like, okay, I have a bad sample. I don't want my generative model to be generating samples as those, but if I throw this away, I'm losing all this information. This bad sample has like information about the world, like what kind of objects appear in the world, or what's the structure of the image, and so on. And like people like usually, they err on the safe side. So what they do is they usually like are very strict because they actually care about like the quality of the image that are getting generated. So they end up throwing away a lot of data. And you lose all of this diversity and all of these samples that were bad, but still were like somewhat useful. Cool. The final thing that we talked about, I think in this workshop yesterday, and maybe there are like more talks about today, is like this privacy and copyright concerns. When you train like these images on the web, there are all sorts of images that have like copyright, they're copyright, and you don't want to be able to like to generate these images. Ideally, you wouldn't like to train on these images to start with. And the situation gets actually very worse because like the models, these diffusion models that are the state of the art for generating images, they memorize a lot. So here's a fun experiment we did with Adam and a few other people. We make a very small data set of 300 images, then we train a diffusion model, and then we generate images, and then for each one of the generated samples, we look at the nearest neighbor in the data set. And congratulations, you invented like a copy machine. You know, this is not a generative model. The only thing that we managed to do here is we managed to like just copy the training set, and this is not useful. And I hear your argument. You might say, okay, this is like very synthetic. It was only 300 images. This is why you memorize them, blah, blah. So then I'm like, okay, let's do an experiment, a more real scale experiment. You go on this like state-of-the-art diffusion model. I guess it was state-of-the-art 2 years ago. But anyway, so there is this amazing stable diffusion model, but they don't tell us what is the training data set. And we think that they trained on Lion, which is a data set that has like a lot of problems, and we want to test our hypothesis. So here's what we're going to do. We're going to get an image from Lion. We know this image is on Lion, and we want to know if they use it to train or no. So we're going to put a big black box in the image, like hiding the face, and we're going to ask the model, can you please fix it for me? I have this image is corrupt, it has a big black box, can you fix it for me? And this is what the model outputs. The model is like so confident that there is a solution to this problem, and the solution to this problem is exactly a training point. And I think this is like a very good argument that this image was used in the training set, and it did not happen one time, it happened a lot of times over a lot of different images. Okay, so these things happen at scale. These models have been trained on like billions of images, they still memorize, and they still have all these issues. Cool, so for a bunch of reasons, I hope I convinced you, creating and making these large-scale data sets is actually like challenging. And what I want to argue today is that good models should use bad data, because bad data are like cheaper to acquire, they usually don't have these copyright issues, and you can get tons of them, but we should use them wisely, because we don't want to be like generating images that have like low quality. Okay, so that's the talk, what the talk is going to be about. So before I actually talk about how we do this, let me show you some results. Okay, so I'm going to start with this result. So on the left, you see like a state-of-the-art model trained on ImageNet, and this is like a generated sample there. And you can see that like it's blurry. That's because some of the samples in the training set were blurry. On the right, you see what you get when you train with the data, but using them as bad. So you have a training algorithm I'm going to talk about today, where like when you train with this data, you used all the data. You did not filter out anything, but you accounted for their corruption. You're like, some of the samples in my training set, they're not always coming from the same distribution. They might be coming from a tilted distribution that has corruption. And this is what you get.
So you didn't mark this strategy?
I will talk, like it's not bad or good. It's like it's a continuum. Like badness is a continuum, and we're going to talk about how we actually, no. No, they're actually bad. Like these are like if you go back on ImageNet, you're going to find some images that are like not great. But when you actually train, usually you treat all of the samples as the same. They're all from ImageNet, so people are going to just train on them. And we are like, okay, they're all from ImageNet, but there is like different qualities inside that data set. And when you train your model, you have to account for these different utilities, these different like qualities. And if you do, you get like better samples. This is another example. I love how like the blurriness of the ship turned into a sunset here. So the model cannot generate blurry images. So it's like, okay, what is this blurry thing? I'm gonna make it a sunset. And this is another example with a bird. So you see this all over. Like if you use like this model, I want to emphasize, it has exactly the same number of parameters, exactly the same data set, exactly the same optimization process. The only thing that changes is how you use the data. So it's just like one line changes the how you train your model, and you can get these things. And you can even do it with like text-to-image models. So you can like have a query that says like, hey, generate me like a fire-spitting dragon, blah blah. On the left, you would get what you would get if you normally train on these data sets. On the right, you get like what you get by actually accounting for the corruption that there is in your training set. And just there is no extra data here. Okay, it's just the same data set, just better optimization process, better like training algorithms. Cool. Some more examples. I think you can like see that it gets better. Okay. So how do we do this? Okay, we're gonna enter like the technical part of the talk. I'm promising to not tire you too much. I just wanna give you like a high level of like ideas. And I think the way it happens is actually kind of fun because we start by looking at a very, very, very simple like corruption model where the images are noisy, but they are actually noisy without the Gaussian noise. So we're not talking about blurry images, like severely compressed images. We're just talking about images that are actually like have been corrupted by a very toy process, which is the process of adding additive Gaussian noise. And then this allows us to develop some math and to study the problem and to derive some nice conclusions. And after we do this, we can generalize this framework kind of easily to arbitrary corruptions. So this is the framework. And once this is in place, I'm going to tell you about how you get some results. Particularly, I'm going to show like some more results on images, and then I'm going to talk about proteins, where like the problem is actually synthetic data. You want to use synthetic data. Cool. Okay. Sounds good? If you have questions during the talk, feel free to interrupt me. Okay. Perfect. Okay. So let's start. I'm going to spend 2 minutes giving you a background about this type of generative model, which is called diffusion models, which is a state-of-the-art model. Like people have like tried a bunch of different approaches, but now we have kind of converged. So when you want to train like a model for generating images, you usually use a diffusion model. And the way diffusions work is that you want to sample from a distribution. We call this distribution P0, which is a distribution of interest. And this distribution is generally very complex. Why is it complex? It lives in high dimensions, it's multimodal, and so on. And you have some plugs to the distribution. But because it is very complex, what you're going to do is you're going to like think about some easier distributions that are the smooth distributions where like you convolve your density, your P0, with a Gaussian. So you get these distributions that are kind of easier. At the end, you're going to have like a pure Gaussian distribution. But you have like this intermediate distribution that have like different levels of noise. And what you actually want to do is you actually want to like kind of reverse that process. So you want to start like from this very, very easy distribution that almost looks like a Gaussian, sample from this, and then use your samples as a warm start to move to the next distribution and the next distribution and the next distribution. And there is a beautiful mathematical theory that says that if you actually want to do this, what you need to do is you want to run a differential equation. And to run this differential equation, what you need is this object. And this is where all the learning goes, is about learning this object, which is called the score function. And it really is like the gradient of the log likelihood of these intermediate distributions. So take a step back. We wanted to sample from this complex distribution of like real images. Then what we did is we like consider these easier distributions that come from convolving your density with a Gaussian. And then like you can actually reverse that process. So you can start with a very easy distribution, use the samples as a warm start, move on to like the next distribution, all the way up to the distribution of real images. And to do this, you want access to this core function. Okay, so that's all that you're going to need about diffusion. And like the cool thing about this core function is that to learn it, all you need to do is you want to learn a denoiser. Okay, this result is called Tweedy's formula. And it's going to allow us to abstract away all of these like diffusion models and like stochastic differential equations and just think about denoisers. So the problem is really like you have like some noisy images. There are different levels of noise. We call these levels of noise, we denote them with T. Higher the T, the more the noise. And then what you want to do is you want to learn this conditional expectation of x0 given xt, which is like your best prediction for the clean image given the noisy version of it. And that's all what diffusion models do. They learn all of these denoisers at different levels of denoising, and then they use them to start from Gaussian distribution, go all the way to the distribution of real elements. Cool. And how do you learn a denoiser? Pretty easily. You corrupt the images. So you create these pairs of like xt is your corrupted image, x0 is your clean image, and then you train the model to restore. So you train the model to go from the corrupted image to the clean image. Simple, right? Okay. So that's what's normally done. Now let's enter adversarial land. This is where things go interesting. I told you that my talk is going to be about like corrupted data. So here is like a simulation of a corrupted data world where we never see like a clean image. We never have access to any clean image. Instead, what we have access to is we have access to this intermediate distribution. We're going to be calling this PT nature. Nature decides to give us samples that are noisy, all of them. They're noisy by taking like a clean sample and then adding noise at a particular level. And we only have access to this noise distribution. And then the problem is the same. We want to be able to generate images not from the noisy distribution, but from the clean. So the setting is you only have noisy samples. Can you learn to imagine how the samples would be without noise, without ever looking at a clean image? Surprisingly, this problem is solvable. It's not trivial in the beginning, at least it wasn't for me when I first looked at it, but it is actually solvable. The catch is that you need a lot of samples. You know the level of noise, yes. Yes, exactly. You know that it's a Gaussian corruption model. It's a very simple model, and then you know exactly how much noise you have. Given these two assumptions and enough samples, you can actually learn to generate samples without ever looking at a clean image. So there is an easy information theoretic argument about why this is possible. It's less trivial about how you do this. How you do this with models like diffusion. Cool. OK, so how do we do this? That's going to be like the secret sauce of this method that we're going to be using across different things, proteins, images. We're going to be generating dragons, and so on. So what is the secret sauce? The secret sauce is that I told you that in diffusion models, you want to learn a denoiser, right? And you want to learn a denoiser for all these different noise levels. So you want to learn it for noise levels that have more noise than the noise that you are given your data set. So nature gave us samples at T-nature noise level, and we want to be using like denoisers at higher noise levels. And you're also going to be learning denoisers at lower noise levels. So these are two separate problems, and we treat them like separately. The second, the learning denoisers for lower noise levels, is harder, and I'm not going to talk about how we do this today. But if you're interested, we can chat over the break. But I'm going to give you like an intuition about the first one, which is how do you do this for noise levels that have more noise than the noise in your data? OK. So here's what you can prove. You can prove this interesting result that says the following thing. OK. What you want in life is you want a denoiser that denoises all the way to the clean images. But you have never seen a clean image. So it's kind of like, how do you do this? OK. It's not trivial. But what you can actually do is you can learn a denoiser that denoises to the noise level of the data that you are given. Because you had some images that were noisy, and you can always add more noise to them and learn a denoiser to go back to this noise level. So you can learn the object on the left-hand side of this equation that says, if I'm giving noisy images, I can always learn to go back to the level of the noise that I was given. Turns out that the object that you care about, the conditional expectation of x0 given xt, is actually very related to the object that you can learn, which is the conditional expectation of xt nature given xt. And that's what allows a lot of this magic. And if you want to give an intuition to yourself why this is true, it is true for the following reason. Intuitively, if you want to remove noise, you want to find the direction of the noise. And if you want to remove more noise, you just have to rescale more. And this is what allows this kind of thing. And you can prove that this is true. And now this kind of gives you an algorithm. And the algorithm is very simple. On the left is what you usually do. What you usually do when you train a diffusion model is you corrupt your images, you make these noisy images, and then you train the model to go to the clean images. What's the problem of that? We don't have x0. In our setting, we don't have a clean image, so we cannot train with the objective on the left. Instead, what you can do is you can do something else. You can train your model to denoise to the noise level that you were given, and then you can do this shifting and rescaling to go all the way back to x0. So you can write down an objective on the right that does this thing for you. And the two objectives, given enough samples, they're going to have the same minimizer. But the nice thing about it is to run the thing on the right, you don't need clean samples. So you can learn a denoiser that denoises the clean images without ever looking at a clean image. And this is, you have to know what? You have to know the noise levels, yes. You have to know the noise levels.
No, and you also have to require the noise to be completely independent of your image.
Yes, the noise is Gaussian, exactly.
Gaussian independent across all.
It's not at all trivial how this generalized to arbitrary corruptions and dragons, but we're going to get to that in a bit. But for now, we're starting a very toy case where like your noise is Gaussian, you know exactly how much noise you had, like you know the sigma t nature, like the noise level of nature, and then you also know like the level of denoiser that you are learning at. No, as long as the level of denoiser that you are learning at is greater than t nature, you can like do it with this objective. Cool, and it's just for Gaussians. Cool. Okay. Okay. Now, what's going to happen in reality in a data set? We're going to have like data points that have different levels of noise. It's not going to be Gaussian noise, but let's abstract it away for a little bit and just think that they're going to be a bunch of points that have different levels of noise. Okay. So Costis, because like my postdoc advisor, I made his image like very noisy, but then you have some other samples that have like less noise. Okay, and then you have all these samples. And then I talked about different data utilities. So one way to think about data utilities is that like images that are very noisy, they're only going to help you learn denoisers for more noise than the noise level they have. So they're going to be helping you learning a subset of the denoisers that you care about. Instead, if an image is like less noisy, you're going to use it to learn all of the denoisers that have like more noise than the noise level that it has. And because it has lower noise, they're going to be allowing you to be learning more denoisers. So that's kind of a cute concept of like the utility of images. Noisy images, they only like help you learn a subset of the denoisers. Less noisy images, they allow you to learn more denoisers. So that's kind of what it is. But it is, everything here is like Gaussian noise. Okay. Cool. Okay. There is a problem, and the problem is that there is a small subset of times where you don't have a lot of data because you only had, let's say, 100 clean images. So there, like, you are relying only on a few good data points. For the denoisers that are close to the noise level 0, you're only relying on a few clean data points. And there's the question of, like, how many do you need? Can you do it with a few of them? And then there's the question, what if you don't have any? The second one we're not going to answer today, but let's think about the first. Okay. I'm gonna go to that now. Yeah. So now let's get to how many samples you need. Okay. So to do this, let's talk about like a very like simulated setting where like there are two sets. There is the cheap set of like low quality images that is like very big. You can think of it like, you know, someone is giving you like photos from their Nokia phone, and they have a bunch of those. And then you also have like a small set of like high quality images coming from a photographer, but those are expensive, so you can only get a few of those. Okay, so you have like two sets. One is the high quality set that is small, and then you have the low quality set that's like very, very large. And then like the algorithm is gonna be very simple. For noise levels that have like more noise than the low quality set, we're gonna be using all of the data, using like the trick that I showed before for the noisy data. And for the noise levels that correspond to lower noise than the bad set, we're only gonna be relying to the good set. Okay, so we're gonna be having fewer data points there. Okay, and let's see how this works. First experiment is the following. We want to see what is our ground truth. So what is our ground truth? We train models on like 3 academic data sets, CIFAR, ImageNet, and a data set of faces. And then we report the performance if you have all of the samples, okay? And here, like, this is a measure of distance of distribution, so the lower the better. So like a few years ago, maybe 2 years ago when we wrote this paper, or maybe 1 year ago, I don't know. We had like these numbers, and these were like the state-of-the-art numbers. Then we do like this nice experiment where we say, what happens if I replace all of my data set with noisy samples and then use these techniques that we developed? And then you see that the distances go very high, which means that it didn't work that well. The reason it didn't work that well is because we didn't have enough of these samples. They were noisy, yes.
These numbers are some sort of measure of accuracy?
It's measure of distance, so like higher is bad. So when you only use noisy samples, the numbers become like really bad, depending on how much noise you have. But for this particular noise level that we are considering here, the numbers become really bad. And then we're like, okay, what if we use clean samples but we have fewer of them? Okay, so let's say that we take our data set and we only keep 10% of it, And then the performance is also really bad. And this is because these models are data hungry. So this is making a point. These models are data hungry. They need a lot of data. If you only give 10% of the data, so the performance that you're going to get is going to be pretty bad. And now the surprising thing. If you use a combination, 90% of your data set being noisy and 10% of your data set being clean, you can almost recover all the performance. So it is a very surprising fact because 10% clean did not work. 100% noisy did not work. But this combination of like a lot of noisy samples, 90% of your data set is noisy and 10% of your data set is clean, actually works really, really well. And the reason it works really, really well intuitively is that different samples have different utilities. The clean samples are going to allow you to learn details, to be generating these amazing images. But they don't have enough diversity. They don't know a lot about the world because you don't have enough of them. So you need the noisy samples to anchor yourself about like what does the world look like? You know, what kind of objects are in the world? What kind of scenes? So this combination works really well. Exactly. Yeah, exactly. Because 10% clean, even though they're coming from the same distribution, it doesn't work. You need a lot of, yes? No, we use our training method because our training method allows us to be using noisy.
And
if you use 90-10,
standard one, you just treat them.
Yeah, you get terrible scores because you start generate 90% of the times you generate noisy images. So you're, yeah. Go on, cool. And then the other interesting thing about this, and then I'm gonna move to like how do you generalize to arbitrary corruptions on the web and proteins, it's gonna be like that you can use this to extract prices. So here's how you do this, okay? The first step is you train 200 models. So that's like a very painful step, but you can actually do this. So you can like simulate all of these different like types of data availability and train different models at different like mixes of like, I don't know, I have like 30% clean data and then I have 50% noisy data at this noise level at this particular data set. So you can like get all of these settings and then train models and then measure the performance. And then you're gonna be like, okay, if I am a data provider and I have some noisy images and some good images and I wanna price them, how should I price them? And you're like, if I wanna assign a fixed price, then it has to start to be reasonable, right? So what does it mean reasonable? It means that like, okay, I look at two performances. So the red thing is like what happens when you have like 70% of your data set that is clean and nothing else. And the green thing is what happens when you have like 50% of your data set being clean and 50% of it being noisy. And you look at these numbers and you're like, okay, it looks like 70% clean, just this, it performs worse. So if I were to price these images, I would have to price like this combination lower than the combination that I get, but 50% like clean and 50% noisy. And you can derive all of these inequalities, and they can actually extract like prices that would hold under a fixed pricing scheme. And you would be like, okay, it looks like on ImageNet at noise level like 0.2, a clean data sample is at most 1.75 times more useful than a noise data sample. It's kind of interesting. Okay. Okay, so all of that is fun, but all of that is like toy. Because we're talking about like additive Gaussian noise, we're talking about noise levels, and then there is a big step, there's a big leap of faith about how do you take these techniques and you generalize them to arbitrary corruptions. So yeah, images on the web, they're arbitrarily corrupted, and we want to be able like to use these images instead of filtering them out. Like the comparison point would be what happens when you take these images and you just throw away the bad ones. But as we saw before, when you only keep good samples, it's not working that great. These models are data hungry. So instead, we want to use all of these samples, but we want to use them wisely. We don't want to be generating these images. So to do this, let's play a game. Okay. So here's the game. We're going to have two images. One of them is clean, and the other one is a blurry image. These are both images of Antonio Taralba from MIT. I thank him for allowing me to put a blurry image on the slides. And then we're going to be playing this game, which is the following. You're going to try to predict which image is the blurry and which one is the clean. Okay. So let's start with this easy task. Raise your hand if you think that the image on the left is a clean image. Okay, perfect. Okay, good. Nice. Now, let's make it a little bit more interesting. So what I'm going to do now is I'm going to start increasing the noise level. And I'm going to be showing you these two images, okay? And one of them is blurry plus noise, and the other one is clean plus noise. Now, raise your hand if you think that the image on the left is the clean image. Cool. You did not get fooled. Perfect. Okay, let's try again. What happens now? Raise your hand if you think the image on the left is a clean image. Okay, now I see like we're more split. And the image on the left is the clean image. But let's make it even harder. What do you think now? Like, do you think the image on the left is the clean image? Raise your hand if you think this. Okay, I think now we're like very close to 50-50. So where is this going? This is going to like the following thing. The blurry distribution and the clean distributions are different. But if you start adding noise to both of them, they start becoming like closer. In the limit, they're both going to become like Gaussians. So what does that mean is the following, that we can like take blurry samples and use them as good samples plus noise at a high enough level of noise. So even though the corruption is arbitrary, what we're going to be doing is we're going to be treating them as good samples plus a lot of noise. And this is going to allow us to be using all of the techniques that we developed before. Yes. Yes, exactly. So there's like the actual noise here is blur, but it can be arbitrary. And then I don't know what it is. I don't know how to use them. But instead, I'm saying like if I put enough noise in them, they're going to becoming like good samples plus additive Gaussian noise, and I'm going to be able to reuse all of my framework. So that's kind of the idea. If you want some like more intuition from signal processing why this is the case for Gaussian blur, you can think of like the power law that happens in real images. So real images, if you look at the energy of their spectrum, it follows like this power law. So it goes down exponentially. And then when you add noise, what you do is you add a constant line on the Fourier. So essentially what you're doing is you are killing the high frequencies. So this, like, because the other frequencies, they have a lot more energy, so they don't like get, from the noise does not impact them. But what you're actually doing is you're killing the high frequencies. And that's exactly what blurring is. So blurring is the killing of high frequencies, and addition of noise is actually doing something very similar. You're losing all these high frequencies. And this is why this method works well for blur, and it works like less good for like other corruptions. But still, if you add enough noise, you're always going to be doing this, but it will boil down to filtering at the end of it, because you might want to add like infinite noise, and then you don't get any signal. Cool. So yeah, here's the framework in pictures. You have an arbitrarily like blurry image, let's say, and what you want to do is you want to decide how much noise do I need to add in order to make it look like a good image plus noise. And if I can do this, I can reuse all of my previous like toy framework that I developed for additive Gaussian noise, because the same tools are going to hold. So the game is like, how do you know like how much noise to add? Like, I don't know, like, do I need to add like how much, what is the variance that I'm going to do? And you can actually train a model to do this. So the recipe is actually like very simple, and it works like in the following way. You find your favorite samples. This is the samples that you actually want to be sampling from, and the worst samples. And that's easy to do. You know, like you can ask Clip, you can ask a user to give you like some annotations of what are the best images in my dataset, what are the worst images in my dataset. Okay, so you create these two sets. And then what you do is you make the classifier play the game that you were playing before. So you give to the network images that are either blurry images, corrupted images plus noise, or clean images plus noise, and the network has to decide, is it coming from the good set or the bad set? So this is the training process, like it's the game that we played. You corrupt images with different levels of noise, and then you ask the model to decide where they're coming from. And then after you have trained this model, you use it to annotate. So you play this game. You start with a bad image. You show it to the network. You're like, do you think it's corrupted? And the network initially is like, yes, it is corrupted. And then you start adding more and more and more noise, and the network becomes more and more confused. And the first time that it actually is very close to being completely confused is the noise level that you add. OK, make sense? Cool. OK, we are done with the technical part. So now let's get to the fun part. Yes. Yes. Yep. Yeah, so it like there is, okay, that's a good point. Like there are certain corruptions, for certain corruptions that look more like blur, that the high frequencies are messed up and the low frequencies are like fine. This technique works great because you need to add a little bit of noise, and things are gonna work very fine because like you just kill the high frequencies with a little bit of noise and everything is good. If your corruption is like different, this technique is gonna work less good. But the worst thing that can happen is that you can filter out the sample, which is what people are already doing. I think a very bad corruption is the corruption that you have like one pixel that is like masked. Because no matter how much noise you add, you're gonna have an image that like everything is gonna be, like an image, and then it's gonna be a pixel that's gonna be masked. So the classifier is gonna need to add like a lot of noise in order to confuse it. And for masking, it's not gonna work that well. But for things that look like, I don't know, motion blur, JPEG compression, these things are like more like corruptions of the high frequency thing, and this method performs. Yeah, we're gonna get, it's the same idea. The question is like, how much do you need to additionally corrupt? And maybe the answer to this idea is that maybe for proteins or for sound or for something else, you need to corrupt a lot more than what is already corrupted, because we start with a blurry image and then we add noise on top of it, right? So if we add infinite noise, we are losing all of the signal that there is. So we throw that away. And it's a matter of like, yeah, how well does it work actually in practice? Yes.
I guess I have a different take on Chavi's question. Is there something about the image itself and knowing that neighboring pixels are of certain type or whatnot, or the way you perceive it or the way the model perceives it, that makes this work better in images than in other cases where the neighboring pieces of data, whether it's sound or survey questions or text, are not as important?
Yeah, I think the answer is yes. The answer is that like the way that like your samples are actually like corrupted, like if the images have locality, so the corruption, if it's blurred, it's just like messing up neighboring things. So this is gonna work better in this case. In cases where like the corruption is more arbitrary and the samples don't have structure, like the one like nice like spectral property that I showed, then this is gonna work less well. And how well it's gonna work, like it has to be figured out. But the good thing about this is that the worst thing that can happen is actually you go back to what people actually are already doing. And what people are actually already doing, they filter their samples. So this, if it is a case like the one that you're mentioning, it's gonna add infinite noise. So you're gonna get back to filtering. But you might hope that it's actually gonna be able to do it without adding infinite noise. And it turns out to be the case for images and proteins that I'm gonna show you now. Okay, cool. Yes, these are some of the results that we were showing before. This is how you obtain it. So you like go to ImageNet, you find like the best images in ImageNet. You ask like a model, be like, what are the best images here? It finds you like some set of images, and then you're like, what are the worst images here? It finds you another set of images. Then you train a model to perform this classification. Then you use the model to annotate. Then you run your new training in this setting where like you have samples at different noise levels. Turns out this works pretty well. So both like visually and like if you look at numbers, like quality scores, like distances to distributions, there is like improvement all over the board. And it works really, really well. And this is actually a hard task because people have beaten this to death. It's like image generation for ImageNet, it's actually a very hard task. Being able to get improvements here is not trivial. And yeah, also for text to image, you can actually get like higher quality by doing these kind of things. Okay. These were all for images. So a valid question is like, does it work well for things beyond like natural images? Does it work well for science to start with? So let's look at this nice application that we have been working for a year now with Adam, which is the application of like, you want to be able to be generating protein folds. So for context, proteins, there's like an amino acid sequence. That's like a sequence of letters, the amino acids that this protein contains, and then this gets a 3D shape. Okay, and the 3D shape is what you're targeting because the function of the protein depends on the 3D shape. So you want to be like generating 3D shapes that you haven't seen before. So you can like design drugs and do all this other stuff. So the problem here is that getting the 3D shape of a protein is actually super expensive. And it's what I was talking about earlier, it's actually a PhD. So finding what is the 3D shape of a protein, you have to like make the protein in the lab, you have to have like all of this expertise to actually make the protein, you have to shoot X-rays, you have to use the diffraction data to understand how the protein looks like, do a bunch of like computational processing on top of it, so it's actually really, really, really hard. Instead, what is easy is like getting the sequence of a protein. So finding like what are the letters, what are the amino acids is easy, but finding the structure is like really, really hard. And this gets us into like this asymmetric situation where we have like, for real proteins, we have maybe like 20,000 of like samples. These are actually proteins that people went to the lab and made them. So there is this nice repository called the Protein Data Bank, and people like made all of these proteins, and they put them in this repository. But then we have like, I don't know, like millions, 200 millions of sequences, but we don't know the structures, and we want to be generating structures. So enter synthetic data. So what do we do in that setting? And this is actually what state-of-the-art models are doing, is you are going to ask a model to find the structure from the sequence. So you use like the 20,000 structures and sequence pairs that you have to train a model. Let's call this model AlphaFold or some other like folding model. And then you have a lot more samples that are like just sequences. And then you ask AlphaFold and you're like, can you please imagine how the structure looks like? And now you have this gigantic database that is exactly in the same setting as we were talking about before, because you have a small set, 20,000 samples that are PhDs. And then you have a gigantic set, 200 million samples that are synthetic data from AlphaFold. So it falls really nicely into like this categorization that we were doing before. The problem is AlphaFold is imperfect. It's imperfect because it's a model, it has all these like learning errors. So a lot of these samples are actually like corrupted. But the corruption is arbitrary, is not known at all. It's not blurry. It's, you know, it's a lot of learning errors that we don't understand what these learning errors are. And it's also not independent. For example, it struggles a lot with long proteins because we don't have a lot of like long proteins crystallized. So the model is not trained on that. It's out of distribution. So it struggles a lot with those. And it struggles a lot with complex proteins that have like multiple domains. So for short proteins, it's great, but for long proteins, it's not that great. And what do people do? They do filtering. So they go to all of these proteins. AlphaFold gives you like a measure of self-confidence, how much do you trust it, and they filter out the low confidence one, and they train the rest. This results in this like bad situation. That was like the state of the art, I think, a year ago. And then what you look at here is you look at two metrics. One of them is quality. In protein land, they call it designability. And the other is diversity, which is really like how diverse are your things that you're generating. And on the horizontal axis, you have the sequence length. How big is your protein? And what you see is exactly what I was talking about. Like the bigger the protein, the worse it performs. In both designability and diversity, you're predicting like less and less diverse proteins, and they are like lower and lower quality because this model is not trained on this data, so the predictions there are not great. So that's the issue. And then, you know, there is like, NVIDIA tried a lot to solve this problem. They have an ICLR oral where they try to like make a massive model and like try to do like different like data processing things and filtering and like all of these like fancy pipelines to do a little better. And they actually managed to perform a little better. But still, like the pipeline is exactly the same as before. You have like this bad data from AlphaFold, and all you do is you have to like filter them out, and then you have different decisions heuristically chosen, like how do you filter out? What are the thresholds, or what are the interesting pipelines? And you see that there is a lot of benefit that you get from having clever decisions, but still we're not there. Instead, what we are gonna do is we are not gonna filter out anything. So we're gonna have a data set that is as big as it gets. We're trying to gonna keep like all of the data, but the secret is gonna be that we're gonna be using data differently based on their corruption levels. So AlphaFold gives you these scores. They're called PLDDTs. They're these confidence scores. So if it's very high, it means that AlphaFold believes it's a good protein. If it's very low, AlphaFold believes it's a bad protein. And then what we do is the same as before. We take a protein. If it has like low PLDDT, we add a lot of noise to it, and we view it as a noisy protein. And we only use it to learn a subset of the denoisers. If it has higher PLDDT, we use it for more denoisers because we can add just a little bit of noise to it and view it as an amazing protein that we crystallized in the lab plus a little bit of noise. And then you have all of this data set that you get from this PLDDT to times mapping, and then you train a model. And you get like, I think, very good benefits. So this is like a plot. On one axis, we have designability, the quality. On the other axis, you have like diversity, how diverse are your proteins. And the whole Pareto frontier of designability and diversity is coming from our model. And this is even for short proteins, which is kind of surprising. This is like for proteins up to like 256 amino acids that are not that interesting. Going to longer proteins, the results are even more impressive. Here, what we managed to do is we managed to take a model that is like how many times? Like 10 times smaller? I think it's like a 17 million parameters model, while the original model is like 400 million parameters. And then what we do is the only thing that we change is this mapping between like PLDTTs and times. Instead of like throwing away data, we use all of the data that we have, but we do it by doing this mapping. And in both like designability and diversity, you get a big boost. I think you can be like 35% better in diversity while having the higher designability. And all of this is not coming from the model. It's not coming from the optimization. It's only coming from the data. It's only coming from better use of the data, which is the point that I want to emphasize in this talk.
Question for you.
Yes.
So your assumption about the noise in the image domain is that you're adding independent Gaussian noise.
Yes.
What's the nature of the noise here? And then
We are still adding additive Gaussian noise.
what extent does that really fit the noise that you, is that thought to fit the noise that actually?
Yeah, AlphaFold does not have additive Gaussian noise. If you look at the structures that have low PLDT, they're like arbitrarily bad. But the intuition is that like everything is gonna, if you add enough noise, everything is gonna converge to Gaussian. So the question is like, how much do you need to add? And if it looks like blurred, like in images, you don't have to add a lot. If it looks like AlphaFold, we actually don't know. So like you see that there are a bunch of models that we trained. It's not, we don't have a single model. All of these points correspond to different like ways of adding, like how much noise do we add. So it's like a parameter that you have to either train it with a model to do this, or in protein space we actually like ablated this, and you get different trade-offs that correspond to the different ways to add noise. But yeah, AlphaFold noise does not look like this. It's arbitrary and definitely not independent. Cool. Okay. So conclusions, some limitations about this work. So the main point here is that like data is really, really important. And there seems to be like a fake dilemma of like keeping or throwing away the sample based on like whether the sample is corrupt or no. What I want to argue is that filtering is a very bad idea. We want to keep all of the samples. We're going to extract as much juice as we can from our samples, but we have to be clever about how we do this because we don't want to be like leaking these like bad quality samples into our generations. So the framework that we propose today is like one way to do this, and it's in many ways suboptimal. There were a lot of interesting questions from the audience, and I very much agree that for certain corruptions, this is going to work really, really well. For other corruptions like masking, it's not going to work really, really well. But the good thing about it is that it's general, and it's scalable, and it's like simple to use. So that allows us to experiment and see what happens. I think for future work, there are a lot of things that I'm very, very, very excited about. One of them is, what can we use it for? In science, noisy data is all over the place. So we will be trying to like actually make this useful for scientific applications where actually you have noisy data. And proteins is a good example, but there's like a lot more. And then the other thing is that like sometimes the corruption is like different for different parts of the image or for your sample. For example, like on the web, we have for privacy all of these images that are like the faces are blurred. And in that case, you have a part of your image that's corrupted, but the rest is not. And instead of adding a lot of noise to everything, it would be nice to have like a framework that's like more like patch level noise. And it's like more general to account for different corruptions within the same sample. So with that, I will conclude, and I'm ready for questions. Thanks so much. Yes.
In some sense, you're doing some sort of bootstrapping. You're using your bad data. So could you do this? Could you repeat it?
Yes, that's a great question. I think if you think about it, people in LLM space, that's what they do in some sense when they do these RL algorithms. So in these reasoning pipelines, what people usually do is they have the model generate data, then they score the data, they keep the better ones, and then they fine-tune the model on this. Then they use the model to generate more data, and then they repeat this process. They call this RL for LLMs. And I think you can very well imagine like repeating this process for this model as well, but instead of filtering,
yes, doing your
you're
thing.
going to be using all of the data that you generate, but you're going to be using differently. And this is something that we want to explore. I think it's a great question. I don't know what will happen, but I believe it's going to be very similar to how people do RL for LLMs.
So I'm an economist, just to reflect my inefficiencies and weaknesses.
Mhm.
So in economics, we never throw the data, and we almost always have found that when you have information about the type of error that you are committing, that you can improve much more than just assuming that it's Gaussian.
Yes.
So have you actually think about tailoring this technique to understanding, said, well, my noise is blur,
Yes.
and therefore there's a continuity there. So I may actually do much better.
That's an amazing question. So it is actually 100% true. The more you know is about the degradation model, the better it is. For example, if you actually know that it's blur, instead of having a diffusion process that adds noise, you can have a process that blurs and blurs and blurs more. And you can write down the reverse of that, and then you can show that it works better than this. And if it's not blur, you can show that this works better. But in general, yes, the more you know about what happened to your samples, the better it is, because you can like develop more accurate frameworks that actually target what happened. But it's the issue there is actually like not trivial mathematically to do this, because this framework, everything happened in the Gaussian space. We're just adding noise, okay? But if the corruption is like blur, you have to design an exotic diffusion model where you're actually blurring, and you have to argue about the reversibility of this process. And if it's blur, you can do this. You have actually done this, and we have experiments, and it works better. But if it's not blur, if it's something like more arbitrary, it's not easy to argue about reversibility of this process. So this uses a lot of mathematical properties of Gaussians that make a lot of these things easier. And it's not easy to generalize to arbitrary things, even if you know them. But if you manage to do it, you will get benefits. Yeah. Yeah, you could imagine that there is like you learn the noise process as well.
Yeah, because I was going to say, so you have two ways of estimating the same image.
Yep.
So this is what is called a specification test. I can reject that is blur, what is affecting the image. In other words, I use a procedure with blurring and I get an image, and then I do it without the Gaussian and I get a very different image.
Yep.
That I can say these two things are statistically different from each other.
Yep.
Then at least I can say it's not blurring.
Yep. I agree.
So.
Agree. You can definitely get benefit by knowing what happened and by designing processes that do this.
So am I correct in my understanding that given that like these PLDDTs are essentially a local measure of confidence and you're able to map them to like the right time point, it sounds like basically any kind of scalar value that you can, if you had any scalar value that's like a cheap proxy for data point quality, that you could use that to learn like, you know, what's like the right T for that data point. Is that correct?
That's true. Yes. Like if you actually don't train a model to do this, you also strike some trade-offs. Like it's always better, like if you want to be correct in the sense that like if you actually want to be closer to your samples actually being like something plus Gaussian noise, then you want to be conservative. But if you're conservative, maybe you throw away too much, and maybe the model can work well with a little bit of distribution shift. So it's not like I 100% agree that you can do it.
Yeah.
You have to think a little bit about what are these trade-offs.
Yeah, no, definitely there are trade-offs, and I understand
Yeah.
because like a lot of corruptions are not going to fit the Gaussian model. I'm
Yeah.
just wondering if you've tried playing around with like different ways of getting this kind of proxy for data point quality. Like, for example, in the image case, you could look at I don't know, you could look at embeddings, or you can look at like softmax output and see like, oh, how close is it to like 1, and that maybe like gives you some sense of like how noisy the image is. I'm wondering if you've tried playing with different proxies and trying to map them to the right T.
Yes, perfect. Yes, so for images, we have tried a bunch of things. One of them is you can ask Clip, which is a model that gives you like a measure of quality, and you can be like, is it a high quality image or a low quality image? And it gives you a probability. And then you can try to map the scalar values of probabilities of being a high quality image to like noise. That works really well. It works worse than actually training a model to do it. Then we have also tried about using these methods that do like no reference image quality assessment. So there are methods that like they're not trained. They just look at like image statistics, and they can like NEMA. I think that's not NEMA. IQA is one example of this. So they try to like find from the image itself like how good it is by looking at statistics of natural images. These also work well. Like in the image space, we found that training a model to do this is better. For proteins, we haven't updated that too much.
And sorry, when you train, in the image case, when you train a model, where do you get the supervision for what's high quality and what's low
Okay,
quality?
yeah, so you first ask a model what is high quality, but this model you only trust it for the outliers, essentially. So like you cannot, like the model is not giving you fine-grained precisions if it's like 0.55 probability or 0.65, but if it tells you that like the probability of being a high quality image is like 0.99999, this you can probably trust. So then after you create these outlier sets of very good, very bad, then you can train a model, and then the model gives you what you want.
Makes sense.
So a very high quality image taken by a professional photographer
Yes.
with a really low ISO or very high ISO,
Yep.
you will confuse it with a bad image, but that's fine with you.
You will confuse the bad image under a lot of noise.
Yeah, and it had a lot of noise.
Yes.
But it's fine. I mean,
Yeah.
because you're not relying on having the perfect set.
Yes.
You're relying on saying, well, these are good enough.
Yes. Yeah. There is some robustness to what good or bad is. And all of these things, like none of that I would say is like severely optimized in the sense that I think there are better algorithmic ideas. And we have a few of like what we could do better. It's just I think the first time that we actually have something that you can like try. And just by trying this out, there seems that there is a lot of like value that people people are not using. So now we can devise better algorithms.
Okay. Well, thanks. That was an excellent talk.
Thanks so much.